everyone, in this video I'm going to talk about the 2 to 3 different ways that you could actually use the different variations of the Rydberg formula and come up with a proper answer. So in this video we are just going to discuss the different ways of using the Rydberg equation to come up with answers. So there's basically 2 main methods. You can determine it using magnitudes, which you absolutely have to use your brain for, okay? You can't just plug and chug. Or you can use the math versions, where you simply have to use a calculator. And so just depending on your style, you probably are going to feel that one of these makes way more sense to you than the other. I personally love this version. This is the one I use. I stick with it all the time. I rarely even look at these other equations over here on this side, but please just pick a version and stick with it. I will never say, okay, using this specific formula, blah, blah, blah. Just make sure you understand conceptually what's going on and then how you can use these different formulas to actually apply that knowledge. So let's start off with my favorite one, the magnitude, and then we'll move into the math section. So primarily what you need to know is this equation if you want to do magnitudes. So you have frequency is equal to your R constant all over N1 squared minus 1 over N2 squared. So for this formula specifically, your R value is 3.29 times 10 to the 15th hertz. Remember, hertz is inverse seconds. And then this is the most important part for this one. N1 is smaller than N2 always. Okay, always, always, always. So numerically, if your values are 2 and 5, N1 is always going to be 2, N2 is always going to be 5. So numerically, N1 must be smaller than N2. But let's look at a quick example of this. So if we were going to look at 2 different things, either an absorption of N1 going to N3, or an electron being emitted from N3 down to N1, how would we use this formula? Well, the answer is you use it the exact same way no matter how you're doing it. So frequency is equal to 3.29 times 10 to the 15th hertz times 1 over N1, so that's 1 squared, minus 1 over N2, so that's the bigger number, that's just going to be 3 squared, and boom, done. Okay, now you figure out your frequency. No matter what, your N1 has to be smaller than N2. But here's the thing, your frequency is going to be the exact same number regardless of absorption versus emission. So you need to actually use your brain to be able to say, okay, this electron went from a low energy state to a high energy state. This must mean it's an absorption. Your equation will not tell you that. But you can also say, okay, this electron went from a high energy state to a low energy state, so this must be an emission. Okay, so you just have to know what that is. And we will always tell you the electron goes from 1 to 3, or the electron goes from 3 to 1. So right there in the problem, we're telling you if it's absorption or emission. So for me personally, I think using a different formula to solve for that and use the positive or the negative, it's just too much. Like, you already know that by looking at the problem. Again, this is my personal method. Now, we also mentioned a different version of this on the GChem site, so I want to show this to you. And so this is where we had 1 over wavelength is equal to R over C times 1 over N1 squared minus 1 over N2 squared. And I'll be completely honest with you, I've never used this specific equation ever in my life, even though it's the exact same thing as the one before. I always do this piecemeal. And so what I mean by that is I solve for frequency. Once I have frequency, instead of doing this to try to solve for wavelength, I just say, okay, wavelength is equal to speed of light over frequency. So you take 3 times 10 to the 8th, divide it by whatever number you just solved for. Boom, you're in wavelength. That just works for me. Or if you need to determine energy, you just multiply whatever you got over here, your frequency, by Planck's constant. So you just take that number, multiply it times 6.626 times 10 to the negative 34th joules times seconds, and then boom, you're in energy. So for me, that works the best. I use my one equation, I use my brain to know if it's absorption or emission. But you can also use a whole completely different method. Again, we showed you this on the GChem site, so let's look at that one. So for this one, we had 2 different equations. So I'm going to write both of these up right now. So we had 1 over lambda is equal to R times 1 over, now this is NF squared. That matters, okay? NF, so N final, minus 1 over N initial squared. In this specific equation, we have an R value where R is equal to 1.097 times 10 to the 7th, and this is your inverse meters, okay? A very strange unit. I never use this equation, but that's okay. And so here, NF literally means final, and NI means initial. Now, at the same time, we can also solve this for energy. So if we do that properly, we would see that we have a delta E, which is equal to our R, so that's again our Rydberg constant, and then we say this is equal to 1 over, then our NF squared minus 1 over NI squared. Again, F means final, A means initial. So for this one, you have an R value, which is equal to 2.180 times 10 to the negative 18 joules. And the beautiful thing about this equation is that if you solve for your delta E, so your change in energy, we're just saying the change in the energy, if you get a positive value, then you absolutely know for sure that you have an absorption, or you set this up backwards. It's one of the two. Or if you get your delta E equal to a negative value, then you know for sure that you are talking about an emission. But I just want to go over really quickly what this means, final and initial, just so that we're all on the same page. So again, same example as before, N1, N3, we'll do it again, N1, N3. So here we have an electron on our ground state. We're adding energy to it. We're having an absorption. It's going up to a higher energy level. In this example, we have an electron already up in an excited state. We're going to release some energy in order to go down to the ground state, and this is definitely an emission. So if we are talking about this example right here, low energy to high energy, our Ni is going to be our initial. Where did our electron start? So it started on the ground state, so level 1. Then our final, where did the electron end? It's our ending state, our final state, in this case our excited state, so our NF would be equal to 3. Now, if we were talking about this side, so it does matter what we're talking about for the problem here, what we would say here is that our initial, this time is equal to 3, so where did the electron start? And then our final, where did the electron end? It actually ended in the ground state. So for this method, your Ni and your NF really matter. And that's because it all comes down to this sign. And so if you flip it around, you would end up getting something is an emission, something is an absorption. Either of these methods are absolutely perfect. Both of them work, but you need to make sure that you pick one and stick to it. So you can either do this mathematically, where you're doing something with either lambda or your wavelength, or you can do it with energy over here, or you can do what I do and solve it here either with frequency. You can also do it with wavelength as well. All of these are viable options, but I just want to let you know or remind you that the most important thing is that you pick something and you know it forward and backwards. So you need to know, does it matter if I'm final or initial? Does it matter if my number is bigger or smaller? Yes. It always matters. So please do the best you can with this. Study. Hopefully this is starting to make sense. If not, please email me. I'm happy to answer questions. I'm going to leave you with this one because this is the best equation in the whole world right here. Yes, it is. Okay. Have a great week. Take care of yourself and drink water.